Hi everyone, I'm Rasmus from Karlstad University, Sweden. This is joint work together with my colleague Tobias on timeless timing attacks and preload defenses in Tor's DNS cache. For overview, we're looking at Tor, which is a low latency anonymity network that routes user traffic through a guard, a middle, and an exit relay. So the guard here is able to observe the user's IP address, but not the destination website, whereas the exit relay is able to observe the destination website, but not the user's IP address. Now, when you're browsing with Tor, then it is your exit relay that will resolve domain names to IP addresses, and then it will keep those in a cache locally to boost performance and reduce resolver overhead. What we show in this paper is that we can reliably probe Tor's DNS cache in order to figure out if a given domain name is in there or not. And if that's the case, we can also figure out the exact second that it was added. So why is that a bad thing? You can think of this as essentially being able to determine Tor's destination anonymity set, which is very useful for traffic analysis. So with this in mind, we redesign Tor's DNS cache so that we can no longer ask these types of questions about the Tor population. And the intuition for our defense is that we should not have any shared dynamic DNS state between different Tor circuits. The defense has not been deployed yet. What has been deployed is a mitigation. So if before we could determine the exact second that something was added to the cache, we can now only determine a window when this event might have happened based on some randomness. So for outline, I will explain how our attack and the defense works, and then highlight some of our key measurement results from our experiments with the live Tor network. In the paper, you'll find more information about the mitigation, exactly how did we set up these experiments, and what safety precautions did we take, and what are some of these traffic analysis applications, which is related work. All right, so let me bring you up to speed real quick on Tor's DNS cache, like what you need to know. So one way to resolve domain names in Tor is to send a cell, and in this case it's the resolve cell. What the relay will do when it processes a domain name is to first check if it's in the cache. If that is the case, it will immediately send the answer back to the user, or at least write it to the sending output buffer. Now, because Tor is single-threaded, there's not going to be anything else happening in Tor between you starting to process this query until you're sending the answer back. However, in the case that the domain name is not in the cache, we will have to resolve this concurrently, because we can't just sit around and wait for some 50 milliseconds. So eventually there will be an event triggered by Tor's main loop, and then we can send this answer back to the user. The intuition for our attack is that we want to make this diagram run twice in a row, back to back, with two queries of our choice. So here's the setup. Suppose I'm the attacker here, and I want to figure out if example.com is in the cache or not. So the first thing I will do is I will start by caching my own domain name, evil.com. Boom, it's there. Then I will send two queries and make sure that they arrive at the exact same time and they get unpacked together so that the relay will queue this up for resolving. My first query will be example.com. So what will the relay do? It will check, is it in the cache? No, it isn't. So we'll have to resolve this concurrently, and since we can't just sit around and wait, we will move on to the next query. Now, is evil.com in the cache? Yes, because we just added it there. So we'll get the IP address back. And some 56 milliseconds later or so, then this event triggers, and we get the IP address back for example.com. If you look very closely at the order of the responses here, you'll see that they flipped. So our first query was example.com, but we got the IP address back for evil.com first, as if it ran past the query. Whenever we see that the order switches, we conclude that example.com is not in the cache. And if we see that the order is preserved, then we conclude that it must have been in the cache. So the trick here is that we need to make two requests arrive together and get unpacked together. So how do we do that? Well, we just create a one-hop circuit to the exit, and then we send those in the same TLS record, because then they have to be decrypted together, and then they get queued up in the main loop right after each other. Then we just observe the order of the responses, and when you add this element of concurrency, This is what the literature knows as a timeless timing attack. We implemented this in roughly 300 lines of code, and then we evaluated it in the live Tor network against domain names that we control. So during 10 days, we made roughly 12 million queries. So half of them were against domain names that we knew were in the cache. Half of them were domain names that we knew were not in the cache. The accuracy here is 100%. It works every time. So this is quite scary, considering that it's a low-cost attack that you run remotely, and I can do this on like my laptop with a spotty Wi-Fi, because all we're doing is sending a TLS record and observing the responses at the order. Okay, so we have an attack. What is the defense? So what we set out to achieve is false positives, at least from Tor's perspective, when we're considering an attacker that wants to infer information about the destination anonymity set. So as a strawman design, we could simply remove Tor's DNS cache, with the idea being if there's no shared dynamic state to probe, then there's no attack to speak of. And assuming that we set here the ISP resolver for the exit relay, then I would say that this is an effective but inefficient defense. And some of you might disagree, because aren't we just moving the problem from Tor's DNS cache to the ISP's DNS cache? And while that is true, it is also the key insight here. So if you have to now do similar attack techniques against the ISP's DNS cache, you can no longer conclude that the domain was inserted by a Tor user, because you're sharing this with non-Tor users as well. And therefore you get these false positives, but from Tor's perspective. The main problem here is that this is ineffective, and it will worsen the performance in Tor and increasing latency. So can we keep this same security property while increasing the performance? And the answer is, of course, yes, and here's how. So as the first step, we're going to add a per circuit cache, meaning if I browse a site on a new circuit, it initially starts out empty, and then as domain names are being resolved, then those will be added to my cache. But we're not sharing this across any circuits, so it can only boost performance while preserving privacy here. The next optimization is that we will add a static preload cache. And the idea here is that we actually know what domain names most Tor users will be requesting, because they're browsing according to the same website as the regular web. So we're following lists like Tranco and Alexa. So if we could just put those domain names in a list and then preload those in the relay, then they could be there to boost performance without being dynamically updated and then hurting privacy. So putting this entire thing together then we have to assemble this list of domain names to preload. Then the exit relay is going to resolve those periodically, locally on its own. Then whenever you have a new circuit, you'll first check, can my domain name be resolved against this preloaded cache? If that's the case, fantastic. Otherwise, you will have to use this per circuit cache. And then the final part of this defense is that you need to have the exit relay configure a shared resolver, and the best option here is the ISP resolver based on past research. We evaluated the performance of this preload cache, and we basically wanted to compare it to the baseline in Tor today. So we ran modified exit relays for 3 months after, of course, engaging with Tor's research safety board. And what we find is that the current baseline performance is 11 to 17% cache hit ratios across different circuits in Tor. This number is roughly 80% if you're also considering cache hits within the same circuit. And this is what motivates this per circuit cache in order to retain performance. So how does this compare to a preloaded DNS cache? The answer, of course, depends on what lists are we preloading. So we looked at the Alexa, Tranco, and Umbrella lists, so for example, top 1K and top 10K. And then we also looked at extended Alexa and Tranco, meaning if there's a domain on the list, then we will also make a visit to this website and see what additional domains would you encounter when you actually visit it. So we have more domain names to preload. And what we find is that the regular Alexa and Tranco lists are very ineffective because you're missing a lot of the domains that you actually encounter when you do visit the website, like ads.foo.com, for example. The Umbrella top 10K here is performing similar to the Tor baseline or slightly above. These extended lists for 1K and 10K have roughly 2 to 3 times more cache hits compared to the baseline today, so they're pretty effective. Our measurements also show that we don't need to update these lists very frequently. So even when we're running with a 3-month-old extended list, we still have similar or better performance than the baseline in Tor today. So to conclude, we find that we can reliably probe Tor's DNS cache. And this is a low-cost attack, it's remote, and it's always correct. And the reason why this is bad is because it narrows down the destination anonymity set in Tor, and that is very useful for traffic analysis attacks like website fingerprinting. We then propose this preloaded DNS cache. And the good part is that it's efficient and effective in the sense that it can provide false positives, add some uncertainty. The bad part is that we actually do need to select these preload lists. We need to maintain them, deliver them to the relays. And we also have to stay away from these self-hosted resolvers on the exit relays and instead use the shared resolvers like the ISPs. If you have a better defense idea, don't be shy. Please do get involved. As we take the Q&A here, I'll just leave you this bonus slide with a little bit of a timeline for this work, some useful links, and then I'll flag for this proposal 344 Tor proposal that is going to show up sometime soon, talking about protocol side channels more broadly. So in this work, we just looked at DNS. So that's it. Thank you all.